Hello, everyone. It is a great pleasure to speak here at Early Universe from Home. In this talk, Arthur and I will introduce a new momentum space for the sitter in the Poincaré slicing, which we call the Kontorovitch-Lebedev-Fourier space, or KLF space for short. The reason for this name will hopefully become clear by the end of the talk. So this talk is based on a recent short paper and an upcoming long paper in collaboration with Nathan Belghali and Sébastien Renaud-Pétel. Before focusing on the sitter spacetime, it is instructive to start with an elementary example, a particle on a circle. This toy example will serve as an analogy for what we will do in the sitter. So let's consider a particle on a circle described by a physical state psi, which is an abstract vector or a ket of the Hilbert space, H. The position space representation of this state psi can be found by projecting this vector onto a bra theta to construct the so-called wave function, psi of theta. So I represent this localized wave function, psi of theta, in red on the circle, whose mod square gives the probability of finding the particle at position theta on the circle. So the continuous basis theta is complete and orthonormal, meaning that we can fully resolve the identity operator on the Hilbert space, and that the inner product of two base vectors is non-vanishing only if they are equal. As a result, any state psi can be fully decomposed in this basis. Let's now construct another basis using symmetries. The circle has a SO2 symmetry, or equivalently its universal cover, U1. Given this isometry group, the reducible representations are labeled by the usual angular momentum, m. This momentum variable here is discrete because the isometry group is a compact Lie group. This label defines the angular momentum space representation of the state psi, whose projection on a base element m gives the corresponding coefficient in momentum space. Just like the position space basis, the momentum space basis is complete and orthonormal, so we can fully decompose a state psi onto this basis. And so now that we have two bases, a natural question is, what is their overlap? In other words, what is the change of bases? And this is precisely given by the harmonic function, m projected onto theta, which are nothing but the usual spherical harmonics. These harmonic functions are eigenfunctions of the quadratic Casimir, here j squared, obtained by solving the corresponding differential equation. And so unlike localized wave functions, these harmonic functions are delocalized around the circle, represented here in blue. They satisfy orthonormal and completeness relations, which follow from the Laplacian differential operator on the circle being self-joint. And so finally, these harmonic functions define an integral transform in the following way. This allows us to go from position space to momentum space and back. And so the key point here is that constructing this way the momentum space according to the symmetries of the problem provides an integral transform that diagonalizes space-time isometries. And so in this momentum space, symmetry constraints, dynamical evolution, and analytic structure of observables become manifest. So to summarize, the isometry group for the circle is SO2, with the discrete angular momentum m labeling the corresponding irreducible representations. We have constructed two bases, theta and m, and introduced the harmonic functions, ym of theta, as the change of basis. That also defines an integral transform. And so let's now repeat the same story in the sitter. So the sitter spacetime is defined as a hyperboloid embedded in a high-dimensional Minkowski spacetime. So in what follows, we choose to work in the so-called Poincaré slicing in blue, covering the expanding patch, adapted to early universe cosmology. So the metric takes the form of an FLRW spacetime, with tau being conformal time and running from -infinity in the far past to 0. Let me also recall that constant conformal time spatial hypersurfaces are simply d-dimensional Euclidean planes, RD. As can be seen from its definition, d-dimensional de Sitter spacetime is manifestly invariant under SO1, d plus 1. The symmetries, therefore, are dilatation, D, spatial rotations, Mij, spatial translations, Pi, and so-called de Sitter boosts, Ki. So as before, the quadratic Casimir is given by J squared, where the J's are the base elements for the standard Lorentz algebra. From quantum field theory first principles, the Hilbert space decomposes into unitary irreducible representations. And for scalar representations, these are labeled by a parameter mu. So in the complex mu plane, the possible scalar irreducible representations fall into three categories. First, the complementary series in red, corresponding to light fields, the exceptional series occurring at discrete values in green, and the principal series spanning the entire real line in blue, corresponding to heavy fields in Hubble units. So to recap, the de Sitter isometry group is SO1, D+1, and scalar unitary irreducible representations are labeled by mu. So we now want to identify the analog of position space and construct the corresponding momentum space. However, there is a small subtlety. A Lorentzian theory with a proper vacuum is only well defined when supplemented with the I epsilon prescription, which tilts the in-in contour in the complex conformal time plane to ensure convergence in the infinite past of the time integrals. To avoid carrying this tilted contour throughout the discussion, we instead Vic rotate both branches on the in-in contour. Time then runs from along the imaginary axis. And this effectively maps de Sitter to Euclidean ADS. So the position space basis for Poincaré Euclidean ADS is therefore given by Z, the time component, and spatial coordinates x. We now want to follow the same strategy as for the circle. So we diagonalize a maximal set of commuting operators, here the quadratic Casimir, C, and spatial translations. This defines base elements labeled by mu and spatial momentum k. These states correspond to single particle states obtained by acting with creation operators on the vacuum. Naturally, as for the circle, the basis mu k is complete and orthonormal. That is, we can resolve the identity with an appropriate de Sitter density of state. So the analog of the theta and m bases on the circle are these position and momentum space base elements for de Sitter. And their overlap defines the de Sitter harmonic functions. These are obtained by solving the eigenvalue differential equations for the quadratic Casimir and spatial translations. So the spatial dependence is nothing but the usual Fourier plane wave, whereas the time dependence is given by a modified Bessel function. In fact, this harmonic function can be viewed as the Poincaré de Sitter spherical harmonics and satisfy orthonormal and completeness relations. This fact follows from the differential operators being self-adjoint. Naturally, these harmonic functions define the following integral transform that allows us to go from position to momentum space. And so the integral transform in time is known to mathematicians as the Kontorovitch-Lebedev transform, hence the name Kontorovitch-Lebedev-Fourier space, or KLF space for short. We have finally completed the analogy table between the circle and de Sitter and identified the appropriate harmonic functions on de Sitter. So crucially, the constructed KLF space diagonalizes the de Sitter isometries in the Poincaré slicing. And so with this structure in place, Arthur will now show that KLF space is the natural framework for studying quantum field theory in de Sitter, both perturbatively and non-perturbatively.
Thank you, Denis, for this introduction. Let me now continue with a very important point, which is the role of the complementary series in the KLF decomposition. In what Denis presented, we restricted ourselves to the square integrable functions, because this is the relevant set when one wants to define the path integral. However, in the correlators, we know that they can be more general functions. For instance, for the two-point function generated by a local operator in Euclidean ADS, we can use the Källén-Lehmann representation to decompose it. This has been widely studied in this paper in the context of de Sitter. And we know that this will in general involve the principal series together with the complementary series. This is because this function doesn't have to be square integrable in these variables here. Let's see how it goes with an example. In the case of a conformal field theory in the sitter, where we respect the unitarity bound here, then the two-point function is fully fixed by conformal invariance, and it takes this form. Then the question is this function square integrable? So to see that, we try to take the KLF transform with respect to one of the two variables, and if the integral converges, it means that KLF is enough to decompose this function, and it means that it is square integrable. And we see that the integral is actually convergent when delta is greater than d over 2. So in that case, the two-point function is given by this integral, where this gamma function can be found by performing the KLF transform. And then, because we know the analytic structure of this, it is analytic in this strip, and it has the blue poles in the upper half plane and the red poles in the lower half plane. Then we know that we can close the contour in the lower half plane because of the properties of this guy at mu at infinity in the mu complex plane. And then this function will be given by the sum of red poles. The sum of red poles is not dependent on the regime here. The regime here is just telling you that the sum of the red poles will be given by this integral. But if delta is smaller than d over 2, then you can see that you inverted the hierarchy between delta and d over 2, and then the red and the blue bars actually inverted their positions. And then you see that some red poles are actually missing in the contour, and they've been replaced by extra blue poles here. And consequently, the integral is given by the sum of the red poles, and not all of them, and a sum of the blue poles. And then, in order to obtain the actual physical function, one needs to subtract the extra blue poles and to add the missing red poles. And by construction, since these are coming from residues in this strip here, this will yield exactly contribution of the complementary series. So in equations, the result is like this. Since we restricted our analysis to unitary CFTs, then there could be only a single contribution from the complementary series, and it is given by this. So it's good because we recover the results of this paper. And then you can see that this contribution can be read from the poles of the principal series contributions. More generally, the complementary series contribution can be read as the non-analyticities of the principal series contributions. And since in every known examples, this is a meromorphic function in the mu plane, then we'll assume that there can only be isolated contribution from the complementary series. Well, because of this, one can extend the KLF decomposition. To this aim, we define a new distribution here that we call delta hat. So it acts on the KLF function by analytic continuing this mu indices in arbitrary complex value of alpha, and it also shadow symmetrizes. And then this is completely consistent with this generalized orthogonality relation for the KLF modes here. And then using this, one can expand any function, even if it's not square integrable, only along KLF. And the price to pay is that the KLF coefficient here is promoted to a distribution. So it is in general the sum of a smooth function, which is the principal series contribution, and a distribution, which is encoded by this delta hat here. And so the KLF version of the correlators will in general be distributions. Okay, so let us now define the KLF correlators, because in the case of the two-point function, I just took the KLF transform, but since the path integral is unaffected by the functional basis we used, we can write the actions here and the source integrals here directly in KLF. And then one can define correlators directly in KLF by differentiating these function generators with respect to the KLF modes here. And this defines correlators in the momentum space directly. And hopefully, these guys are related to the real space correlators by inverse Källén transformations, exactly in the case of the development function. And exactly in the CFT case, these correlators can in general be distributions, and then they can in general include some delta hat factors. Okay, so since we have KLF correlators, we can define KLF Feynman rules now. And then at the level of the free theory, we can perform the Gaussian integral explicitly because it is exactly possible to perform it. And then we can find the Schwinger-Keldysh propagators. So since we are using in-informalism, there are 4 of them for the possible interaction between the branches. And then we have the plus plus, minus minus, which are respectively the time-ordered and anti-time-ordered. And they look exactly like the Feynman propagator in flat space. And here we have the 2 Whiteman functions, which are given in terms of this delta hat function. Here we had to define Ipsen prescription that we took from these 2 papers, from Pimentel-Melville and Denis Werth. And this is a bit different than in flat space, because in flat space we will only have this prescription here, but this is not shadow symmetric, so you need to shadow symmetrize and to tune the coefficient so that this correctly gives you the time-ordered propagators in terms of Bessel functions. And then for the interaction vertices, so here I'm considering a polynomial interaction, it gives you this expression here. So you have the usual conserving spatial momentum delta function, which is because of spatial translational invariance. But because we don't have the conservation in the mu space, instead of a delta function, we'll have these vertex functions here, which are defined in terms of multiple Bessel function integrals. So these are the only functions you have to compute in KLF, and these are in general meromorphic functions. Let me now go through a simple example, which will be the single exchange diagram. So I will focus on this diagram, which is the KLF version of the single exchange. You see here it's directly in KLF. I have no space, no time. I am fully in the momentum space. And I amputated the diagram, which means that I am ignoring the propagators associated to the external leg. Here I'm considering the plus plus vertices because it is one of the most complicated diagram here. The plus minus is simpler. And then this is given just by following the Feynman rule. This is given by this integral here. So you see that we have an integral here in the mu. We have an integral in the mu space because we don't have a conservation in mu here. And then this can be performed by closing the contour, because this generates poles here in the imaginary axis, and the Ipsen prescriptions generates pole here in the complex plane. These poles are giving the particle production contribution, so it gives the so-called cosmological collider signal, and these poles are generating the background signal here. So this computation has been performed by Nathan, which collaborated with us in this paper, and it generalizes the computation made by Denis in D=3. So to conclude, let me say that we just found a momentum space adapted to the Sidereau isometries that we call the KLF space for Kontorovitch-Lebedev-Fourier space, and it makes the perturbative computation transparent in this picture, and it opens many future directions, like can we find general statements about causality, analytic structures, can we find the implications of unitarity, such as positivity bounds, can we formulate effective field theory in this language, because in flat space it is formulated better in momentum space, and can we it is the correct language to understand normalization.